Hello, everyone. I'm Jeff Lovell, Pi Innovo. So today I'll be presenting a case study of a real-world use of many of the tools and techniques you've been hearing about. So Pi Innovo, in the project that I'll be discussing, we were responsible for custom hardware and software. This was for a sensor module within an autonomous passenger car. I'll begin with a little overview of the vehicle itself. So this was a traditional passenger car that was retrofitted for autonomy. And many of us in the automotive industry, we have a lot of experience with the traditional EE systems within the passenger cars that were already there. Those systems are still there. The autonomous systems are just an overlay. So we have a number of additional sensors, communication devices, but the rest of the car is still there too. And so there's old domain concepts and new domain concepts busy at work in such a vehicle. Our system specifically, so this was a sensor module. Its purpose in the vehicle was to report some accurate data from a high-resolution wheel speed encoder. That's like a traditional brake system activity within a regular car. This was slightly different from that because so this ECU, it had some additional responsibilities. Yes, we read some wheel position data and we transmit it out to the vehicle, but we're doing so, in this case, over an Ethernet bus. That in itself, maybe not so special, but the other interesting part is we're timestamping that data based on other incoming data from other modules on the Ethernet bus. So that the data has a common time base with the sensor suite for the rest of the autonomy system. The ECU, it receives some basic powertrain data from the traditional CAN bus. It's also present. But in addition, this ECU has a high integrity aspect. We have some internal redundancy built into this ECU so that we're fault tolerant to any single point failure. It's special because it means if there's any fault of hardware or software within our box, we're actually still providing full availability of the wheel position data that's necessary for the autonomy compute platform. So there's this concept of internal redundancy and high integrity within this single ECU. So that's the module. I'm going to talk a little bit about what our responsibilities were within the system. So Pi is acting as a tier 1, and of course, as a tier 1, we can choose to develop things in-house or to outsource, but in reality, almost all of the hardware and software for Pi is in-house at Pi. So we're doing the hardware design, the software design, and application integration testing. The only things we would normally outsource are things like special tests, EMC, things that require chambers and special labs. And also the ECU volume manufacturers through contract manufacturing. So we're talking about a big project. It's custom hardware. It's custom firmware. This was a new microcontroller to us, a different family of microcontrollers. We have our own operating system, but of course we have to port it to this new microcontroller and revalidate all of its major functions. Our operating system includes a software API. And that software API is developed for integration with application software in Simulink. So all of those things we would like to leverage and reuse from the way that Pi would develop normal car automotive systems in this autonomous program. But again, it's new hardware, new microcontroller, and high reliability. So just the focus of this presentation, to put it into context, we're using some of the vector tools for software testing, both in the firmware and operating system. And then mostly what I'll be focusing on is application layer software, VectorCast, using coverage metrics for our code that comes from MATLAB Simulink, which is a little different from many traditional software activities. Yeah, I'll point out that the project schedule was quite aggressive. OEM had a number of motivations to get a product into test as soon as possible. Frankly, it was mostly California car companies that motivate the Detroit OEMs to act faster, and thank you, California. It's good to have a push. But anyway, to get things out fast, we need to know how to reuse what we do best. We don't want to throw away everything. We don't want to do things from scratch when we don't have to. So what are we reusing? We're reusing circuit hardware, power supply, analog circuit design. Okay, things that we can take from other traditional ECUs. The development environment for hardware and the development environment for software. The PC tools that you use to lay out a circuit board, the PC tools that you use to write and test your operating system. And we're trying to reuse as many of these things as we can, of course, to accelerate the delivery of product. And then the test tools as well. And so that's really what we're talking about here is we have an existing operating system that we're porting to a new target. We have existing operating system tests. We want to use the same tests if we can, in as many examples as we can. This maximizing reuse is going to be very critical to the FAST project. Talking about the way that we would develop traditional software for non-autonomous passenger cars. So many V models, every company has one. The Pi Innovo development process we call our business management system, the BMS. But again, a V model process for formally defined steps of quality assurance relating to different layers of documentation and tests. But really, more specifically, I think it's important to talk about what this really actually means for application-level software in the vehicle. So this represents a traditional vehicle system. We would normally break down our V model for the application-level software into a workflow that kind of looks like this. So, of course, we have low-level software requirements. And then the source code that's written against those requirements, that's in Simulink. To put the software in the vehicle, we use the Simulink code generation environment. So that's the MathWorks tool that converts the graphical model-based software into C. And then we compile C for our specific ECU target. But for our unit testing, for our software unit testing of the Simulink logic, we don't really use that step normally. We don't use code generation. We don't use the target. Simulink is a great simulation environment. It's built for testing and putting in signals and measuring outputs and data traces. So we would do unit testing within Simulink itself. And so that's like I've shown here. So that's the way we used to do it. And then autonomous program comes along and high robustness, high integrity. We have new requirements for this high integrity ECU. And so that drove the reason to use these additional tools. So the thing that was new, we required in this project some formal measurement of code coverage. And again, this is the simple concept of ensuring that your test has actually exercised every path of logic within your software. And this is something that doesn't really directly apply to model-based development like Simulink. And where's my path of software? Where are my lines of code? Well, it's a graphical model, and it all gets highly optimized during the build process. So I can't really pick out where are my paths of code in Simulink that my tests are covering. And actually, it's not Simulink that's running on the target at all. We're talking about Simulink to C to a binary to the target. So Simulink is very far removed from that final step. So this is a gap for us. We wanted to monitor code coverage of, in this case, the automatically generated, not human generated, source code during our unit tests. So the old diagram shown a new way. In reality, it wasn't that tough. So we can use the code generation tools the same way we were using them before. We can generate C source from Simulink, but instead of compiling it for our ECU target, we can actually use different settings in Simulink to invoke host execution of that C source. So we'll compile it for the Windows PC instead of compiling it for our ECU target. And we can actually execute the same unit test in that way. The nice thing about that is we're still doing testing using Simulink as the front end. And we can still use the same test scripts and like test plan that we had already been using. So it's still a test in Simulink, but now this is the special part. It's a test running based on the auto-generated C compiled for Windows and then run through the Simulink environment. And that's where VectorCast comes in. So I think you've heard a little bit about the vector code coverage analysis tools. So that handles the step of instrumenting the C source, collecting data while the execution is happening to confirm that this line of code was executed, this line of code was not, presents all that data result into a format that gives you a coverage percentage. So right, these were the different things. I configure Simulink to this mode that MathWorks called SIL mode. I generate C and run it on my PC. My scripts, my unit tests, those things don't change. And VectorCast is tracking whether each line of code was executed or not. As a side point, tool qualification is an important step. So this was a new topic for us relative to how we normally develop traditional automotive systems. We didn't have a code coverage tool that was quantitative in the past. Our method for ensuring our test was good was peer review. And that was a formal and documented process. So we believe that we've always had thorough tests. They're requirement-based tests. We think they fully exercise our logic. We don't have a metric. We don't have a number. We don't have a report at the end saying 80% of your statements were actually executed by your test. So we could have approached that problem by saying, well, we'll build it ourselves. We can find a way to put hooks in the C source in some way to replicate the same things that, in the end, VectorCast does. At the naive beginning level, it doesn't sound so hard. You could always make it sound simple. Even if it were simple, which it's not, we could have built a tool, and then we would have faced the burden of convincing our OEM customer that our tool was bug-free. So now I'm not only developing embedded software, but now I'm developing some PC tool, and that could be full of its own bugs and be reporting bad results. So I'll have that burden to bear. I need to certify my tool and prove that it is good if I were to invent one on my own. It was a big deal to us that this was a tool that was recognized by our OEM. So if I'm using a tool that my OEM is already comfortable with, well, why does that matter? It matters because that saves me 2 months of convincing the OEM that my other thing is good. And, of course, we're talking about a tool that is currently existing. I don't have to build it from scratch myself. So many ways to save time in an accelerated project. So yeah, in the end, it looks like this. So Simulink, it controls the software execution, and VectorCast is monitoring the coverage. At the end, it spits out a coverage report, which is equally important to us as our test result. Again, we're talking about unit testing where we were doing requirements-based tests to start with. So first, I'm going to be looking for my tests achieving a 100% functional pass. That was what we had done before VectorCast came along. I have a set of behaviors that I expect my software to create. If it doesn't match those behaviors, my test will fail, and that was always there. So it's like after I get my unit test fully passing, my behavioral logic is correct. There are no behavioral problems. Then I can check the code coverage. I say, OK, I think all my behaviors are good. Did I actually miss any statements? Is there any part of my code that I didn't actually test, even though everything else that I tested was good? So this is an additional result component. Again, I think it's important to think about it as secondary to the functional result of your test. So if your test doesn't pass, there's no point in looking at coverage. But once your test is passing, then yeah, you can get an indicator of, was my test thorough, in a more quantitative way than you can just through techniques like peer review and documentation. I'll show you a little bit what it looks like since this is a real-world example. So again, this is the auto-generated C. This is what MathWorks code generation spits out. And this is shown within the VectorCast GUI. So after I execute my test, it looks like this. I have columns of results telling me on a line-by-line basis, yes, this was executed, or no, this was not. And I think it's also interesting to talk about this, the blue case I showed as the second bubble. So we're talking about Simulink and autocode generation, meaning the human doesn't actually get to choose what C source code gets generated. You can force it to generate special things on your behalf, but it's going to otherwise optimize and enforce like coding standards that were built by MathWorks. So there can be cases where there's like an impossible branch. If I have logic that would implement like a switch statement, I have an input, it can have 3 values, 0, 1, or 2, and I have logical behaviors that will be invoked whenever it's one of those 3 values. That's all the logic that I would probably put in Simulink. I would say enumeration 0, you go and do this thing. 1 and 2, you go and do these other things. Maybe I have even more protection logic inside Simulink saying the input parameter to this can never be more than 2. So I'm going to have like limits on my input values to make sure it's never out of range. Maybe I did that for thoroughness or another reason, whatever, but in Simulink, of course, you can make that choice. You're saying the input data, it is saturated. It can never exceed 2. MathWorks code generation, it's actually going to generate a switch statement, and they have a standard, which I think is a good one, to always include a default case in a switch statement. So the generated C, which again, I'm not writing myself, it's going to have things like case 0, case 1, case 2, but it's also going to have a default case. And I can't really execute the default case because I can't feed it logic that would ever pass value 3. I've got things upstream of that that would prevent value 3 from ever getting in. So now we have kind of an impossible case. And I think we mentioned earlier that if we're talking about impossible cases caused by things like hardware access registers, you can stub them and actually find better ways to execute those tests through designing your code through testability. But you're always going to face a case, especially when you're using tools like autocode generation, that you just can't. They're not possible in the unit test environment because you've got other protections to make sure that can't happen in the first place. So the way to handle that in a formal way is it's called coverage by analysis. So it means we're going to put a human in the loop again. But this is very focused. So after all the testing is done, the unit test is passing, I've got a coverage result, I can look at the things that weren't covered. And now I can focus my time on assessing each one of them. So if I find a default case for a switch statement, I understand what's there. I can look at the generated code. I can see, OK, in this default case, it's not actually doing anything malicious. It doesn't interact with any other shared memory, et cetera. So I can say, yes, as a human, I've looked at that line of code, and I said, this line of code is OK. I can make notes on it and preserve those notes. So the second example is the blue A's that you see are where a human has come and said, yes, I realize that case is not covered by the unit test, but I've analyzed it myself. I see that it's safe, and it's a good way to help sort the information from a test result. I've got tests that were covered by execution, tests that were covered by analysis, and then lines of code that simply weren't covered, and those represent the gap that I can focus on later. So in the end, what does it mean? We got to reuse a lot of the familiar stuff. We got to add the code coverage metrics to our development workflow, but really preserve everything else we know and like. And yeah, this accelerated the delivery of the product to the customer, which is really what we needed in this example. So that's the end, and I'll be happy for any questions you have. Sure.
What are the classical?
We have a mic. I'll hand you one.
Yeah, thank you. One of the classical things to test is like boundary testing, right? So if it's 10 or less, do this. If it's more than 10, do that. And so naively, you could have 100% code coverage without testing the boundaries. Whereas when a human constructs a test, you usually say, oh yeah, I want to test 10.00 and it should do one thing, and 10.0001 should do the other thing. How does the code coverage deal with that aspect?
Yeah. Yeah, it's a fair question. So I guess in the end, it just matters how that code is implemented in C. And if we're talking about code generation, it means, yeah, how the generation tool implements that in C. In the end, it will still have an if statement and either a greater than or a greater than equal than. But it will be one specific instruction, one operator. So that is still controlling which path of the if statement it's going to take. It's going to take the true or the false path. Whether you test 10.0 or 10.001, that's not so much to do with the code coverage as, yeah, your actual test script. So that's the guts of your unit test. And I think that's totally valid, whether you're doing code coverage or not monitoring code coverage. Yeah. Hopefully it helped. All right, well, thank you again.